Okay, here we go. Let's talk about step one. And this is going to be reversible isothermal expansion. Okay, so now we know this Carnot, every place has to be reversible. We're always going to start with reversible. Okay, isothermal expansion. So if we look at our piston cylinder that we're going to have here, we are going to have our piston at some state 1. I call this state 1. And we are going to expand it so it comes out here to state 2. Okay, that's where we're going to go, from 1 to 2. And it's going to be isothermal expansion, and let's say this is at TH, and it's going to be equal to constant. So we're going to keep this at a high temperature. Okay, how are we going to do that? Well, first we're going to insulate the sides here of this piston, so no heat can come out the sides. And we know that as expansion occurs, we know that temperature is tending to drop, okay, because those molecules kind of relax a little bit. They get to slow down just a little bit because that pressure is not on them. And so the temperature tends to drop. And so in order to keep that temperature up, what we're going to have to do is we're going to have to connect this to an energy source. That is, so here's an energy source at TH. And that's going to put into here some QH is going to go into this to keep the temperature at TH. So every time the temperature wants to drop, the heat says, hey, no, we're going to keep you at a constant temperature, TH. Okay, so this gas is expanding very slowly. Okay, you are working on the surroundings at this point. All right, so every little temperature drop we want to have, nope, that heat transfer comes in there, brings it right back up to where we want it to be. And so what we want to do is be able to draw this on a PV diagram. Okay, so let's look at it for our two types of situations. Here we have our ideal gas, and we have our water. Okay, so let's draw them. We're going to draw these 4 times, so get used to it. Maybe you want to draw it once and refer to it. I don't care. PV, I'll do pressure, volume, pressure, volume. We're going to have a line of constant temperature we're going to call TH. We're going to have a vapor dome. We're going to have a line of constant temperature we call TH. Okay, now let's label our points. We are going to start here at 1, and we're going to go down to 2. Now the pressure is going to drop, okay, because we're expanding. But we're keeping it at a constant temperature. That's going to happen for a gas. But what happens for water? We're going to say we're here. 1, 2. Okay, in this situation, the pressure doesn't change. We're just changing the volume, making the volume bigger here as we're going through here. So we have to make sure we understand what kind of system we're dealing with, a gas or water, because right here there's already a change. The pressure is changing in one and not in the other. Okay, and that may seem weird to you, but it's important because one, we're changing from a situation that's more liquidy to something that's more vapory, I guess, in that liquid vapor mixture. Ideal gas, we're have a gas, so we're working with this. Now, let's look at this process, and if we would do this, remember it's a closed system, so we'd go back here to our first law. Delta U is equal to Q minus W, right? Delta U is equal to Q minus W. We know we have some work here in these situations. We know we have heat transfer in the situation. We have to. Okay, we have heat coming in to keep that temperature constant. Okay, but there's something that is not going to be the same between both of these equations. And I want you to think for a minute, what is not going to be the same? Work is going to be the same. We may have a different amount of heat here. I shouldn't say the work is going to be the same. What I'm trying to say is there is going to be work in both situations. There is going to be heat in both situations. But there's one thing that's not going to be the same in both situations, and I've kind of got you there already, and that is the internal energy. The internal energy is not going to be something that is going to be common between both situations. Ideal gas, this is going to go to 0, whereas in water, it's not going to go to 0. Okay? Now, why is that? Now, you know the internal energy change is going to happen in water. You're going from a more liquidy mixture to a more vaporous mixture. You are going to be adding a lot of internal energy there. So the internal energy is going to be there. You're going to have mass times U2 minus U1. You're definitely going to have a U2 minus U1. In the gas, that's not going to be the case, because remember, we could still replace this as the mass times U2 minus U1. But remember how we would do this, even if we were doing variable specific heat or constant specific heat. We look up the properties of a gas based upon its temperature. And in state 1, it has the same temperature as state 2, and therefore the temperature is going to be the same, and the internal energy is going to be the same. And therefore, that's why it's 0 here. So that's an important difference between ideal gas and liquid water. Okay, now let's go here to our next situation, our step 2, or our process 2. We had reversible isothermal expansion. Next thing is going to be reversible adiabatic expansion. Okay? And so what we're going to do here in this situation, we're going to have our piston cylinder. It's getting bigger out there. And we're now here at state 2. And we're going to expand to state 3. But we want this to be adiabatic, so we're going to insulate the entire piston cylinder adiabatically. And so what happens here is that TH, now that expansion, there's nothing to bring that temperature back up as it wants to naturally go down, and with the expansions happening, this temperature is going to drop here to some temperature we're going to call this our temperature low, or our temperature cold, or cold temperature. Okay, so we're slowly expanding. We're doing work on the surroundings, but now that temperature is going to drop. Okay, there must be here work that's happening. So let's look here in our diagram that we're going to draw again. We're going to repeat this over and over and over again. So here's our gas. And here's our water. Okay, pressure, volume, pressure, volume. And we have now 2 lines. We have a TH and we have a TC. There's our vapor dome. We have our TH, our hot temperature. We have our TC, which is our cold temperature. And let's draw our points. We said we had 1 to 2. That's what we had before. Here, 1 to 2. It's very important for me that you understand, even though these are drawings and they're not going to be exact and they're not going to be perfect, that you put point 3 over here. Okay? That you put point 3 over here. That's a big deal to me. Why? Because it's expansion. There's going to be a change in volume here from 2 to 3. From 2 to 3, there has to be a change in volume. You have to show that to me. You can't go straight down. You can definitely not go to the left, because that's wrong. That's completely wrong. Okay, so make sure that when you draw this, point 3 is to the right of point 2. Okay, now we're dropping down here. We're going to a different isotherm. We now have our 3 of our 4 states that we're thinking about in our situation. Okay, now in this situation, if you're going to look at delta U is equal to Q minus W, delta U is equal to Q minus W. Delta U here, there's definitely going to be delta U's in both of these, because you're going to have a change in temperature. So the ideal gas, you're going to have to look up properties. And the same thing is going to happen with that water. You're going to have a change in internal energies. We have work. We're not going to have heat transfer here. So that heat transfer is going to go away in both of these situations. So this is going to go away. So now in this time, the equations kind of look alike in process 2 or step 2. All right. Let's go on now and talk about our third process. So step 3. It's going to be reversible. Isothermal. Compression. Okay. Reversible is known because it's Carnot. We went isothermal, adiabatic, and now we're back to isothermal, and now we're going compression there. So if we look here at our diagram, we're now up here at state 3, and now we're going to go back to state 2. State 4. What am I talking about? We're going back to state 4. Okay, and now those molecules, what's happening is the temperature was at Tc, and we want that to be equal to constant. Well, as we're compressing it, those molecules are getting more energetic. They're like, hey, something's going on, and they start moving around some more, and they're going to be increasing in temperature. And what we want to do is we want to not allow that to occur. We don't want that release or that rise in temperature to occur. So we are going to connect this to a reservoir that is a sink at Tc. And so what's going to happen is you're going to have heat transfer leaving this, dumping into that sink to keep the temperature constant. So now what's happening is that external force, the surroundings are working on that system, causing this to happen, and we are going through that process. So here we go. Let's draw it on our diagram. So here's my gas, and here's my water, and we have our PV diagram, and we have our PV diagram, and we have our 2 TH, and we have our TC. Here we have our vapor dome, and we have our TH, and we have our TC, and we look here, and we have our states 1, states 2, states 3, and this is what we're going here. And we have our states 1, states 2, states 3. Okay, that's what's happening. And now we're going compression. So that means we're moving back to the left, and we're going to go up here, someplace here to state 4. Back over here to state 4. Okay, that's where we are. So we should be able to kind of map where we are. If I wanted to get this a little bit thicker here, we're going this direction, down here this direction, back up here this direction. That's where we're going. Okay, that's the direction we're going. Well, we know where we're going to finish up. We're going to finish up back at 1. Okay? Well, what's going to happen there? It's going to be reversible. We did isothermal, adiabatic, isothermal. We're going to be back to adiabatic. And what's happening here? This is going to be compression. So let's write that down. It's going to be our step 4. Reversible. Adiabatic. Compression. So we have our piston cylinder. We are now here at state, state 4. And we're going to move back to where we began at state 1. And we want this to be adiabatic, so we're going to insulate this whole piston cylinder so no heat can leave. And what happens is that temperature cold increases, and I should write it this way just to make it a little bit easier to understand. Temperature cold increases to temperature hot, because now what's happening is that compression is happening. Those molecules are getting more excited, and there's nowhere for that heat to go. So it's going to raise the temperature of that fluid, of that gas, of that water that we have there. That's what's happening. We've completely gone back to our state 1. And so this is going to be our final PV diagram. Our final PV diagram for our gas and for our water, or whatever we're dealing with here. We have our two things. We have our TH. We have our TC. We have our vapor dome. We have TH. And we have TC. Okay? And if I were to draw this now, it's going to look like this. I like to kind of draw the lines beforehand and put here point 1, point 2, point 3, point 4. Those are my 4 states, and this is the direction I'm moving. And this is going to be state 1, state 2, state 3, and state 4. This is the direction that I'm moving. Okay, it's important that you see that there is, between 1 and 4, that there is some compression happening. Okay, I'm going to be very picky on if 4 is to the right of 1 and 3 is to the right of 2. That is very important here. This is how the Carnot cycle looks on a PV diagram. That's how we typically draw them. Okay, you need to know this. You need to understand this. You need to see how these processes work together. Okay, you need to be able to not just memorize it, but look at this PV diagram and kind of understand how that piston is moving in these situations. Okay, that'll end this segment.